We are starting today with a fascinating dynamic that has been driving our research all week. We just watched memory stocks go through a deeply volatile week, the kind of rapid, whipsawing market movement that leaves observers searching for the underlying narrative. And right in the middle of this turbulence, a Chinese lab called Moonshot dropped Kimi K3, a model that lands near the very top of the independent evaluations.
That collision is what sent us digging into the mechanics of memory over the weekend. Because when you put those two events side by side, they surface a genuine structural question. The United States has heavily restricted the advanced compute, specifically the top-tier GPUs, and the high-bandwidth memory that AI relies on at the frontier. The constraints are very real, and they are binding.
Exactly. The hardware bottlenecks are firmly in place, and they have raised the cost and difficulty of training. Yet Chinese models continue to make significant leaps, matching or trailing just slightly behind the absolute best closed models globally on many tasks. How are they achieving this progress given the physical limitations?
That is the core theme we want to explore today. We're going to look closely at the physical hardware, the regulatory landscape, and the deep architectural efficiency. We want to share our reasoning as we trace how intelligence is manufactured and distributed. Quick note. This is education and entertainment, not investment advice. Companies are examples. Never buy or sell calls. Do your own research. Before we dive into memory, we must establish the baseline. Compute comes first. The advanced NVIDIA GPUs are the primary engines of the artificial intelligence boom. The restrictions on those advanced GPUs are well known, and raw compute remains the single largest constraint on frontier training. We are focusing intensely on memory today, because the recent market sell-off hit the memory sector the hardest. But compute is always the foundation.
That is an essential anchor for this entire conversation. The memory is there to serve the compute. When a lab trains a trillion-parameter model, the sheer number of GPU hours required dictates the capital cost and the timeline.
Right, and when those GPUs are restricted, the training clusters have to be built using whatever chips are available, which can mean more accelerators spread across more racks, heavier networking demands, and substantially more power.
The constraints on compute are the catalyst for everything else we will discuss. They do not automatically force innovations into existence. Engineering remains incredibly difficult, but they massively strengthen the incentives and make extreme efficiency much more valuable. So while we will spend most of this episode examining the memory ladder and how the chips communicate, we are holding the reality of compute scarcity right at the center of the frame. To really understand the landscape, we need to calmly map out the different types of memory. It is a spectrum of technologies, and each serves a specific purpose within the hardware ecosystem. At the very top, sitting closest to the processor itself, you have SRAM. This is the tiny, incredibly fast on-chip cache built directly into the die.
Stepping down one rung brings us to HBM, or high bandwidth memory. This is the AI accelerator's immediate working memory. It consists of stacked DRAM sitting right next to the compute chip on the exact same package. Below that is GDDR, which is optimized for graphics processing, and then DDR, the standard memory deployed in everyday servers and personal computers.
Further down the power curve is LPDDR. It is critical to note that LPDDR primarily serves smartphones, tablets, and increasingly AI PCs. While some emerging server designs are starting to experiment with it as data center power budgets tighten, it is not broadly common across conventional data centers yet. All of these formats, HBM, GDDR, DDR, and LPDDR, are families of DRAM. They are volatile, meaning they forget all their data the moment the power is turned off.
Finally, there is NAND, which is persistent storage. When you save a document permanently, it writes to NAND. Understanding what hardware each memory type serves allows us to see exactly where the supply chain bottlenecks form and how they ripple outward. Let us spend some extra time examining HBM because its physical construction is extraordinary and explains why it is so difficult to manufacture. HBM is essentially stacked DRAM. Manufacturers take standard DRAM dies and thin them down dramatically in thickness, not width, but vertical height, so they can be stacked like microscopic floors in a skyscraper.
And they do not just stack them blindly. The entire vertical stack rests on a specialized logic foundation called the base die, which handles communication routing for the layers above it. To connect these layers, manufacturers drill through silicon vias, known as TSVs, straight down through the fragile memory chips. This requires profound manufacturing precision to ensure thousands of microscopic connections align.
Once that vertical stack is complete, it is placed directly beside the AI accelerator on a shared substrate called a silicon interposer. This interposer acts as an ultra-fast microscopic highway. That physical placement on the same package is the defining feature. Because the memory is placed so incredibly close to the compute, the connections can be very short and incredibly wide.
This architecture delivers massive data bandwidth between the memory and the processor, allowing the GPU to be fed data at the exact speed it requires to run a massive neural network without stalling. Crucially, those short, wide connections on the interposer are highly power efficient compared to pulling data from a traditional memory stick across a standard motherboard. For frontier models managing billions of calculations per second, that specific blend of extreme bandwidth and tight power efficiency is exactly what makes HBM the critical component. But that breathtaking performance comes with a severe manufacturing trade-off. Building HBM consumes a completely disproportionate amount of raw silicon wafer input relative to the actual memory capacity it yields. This is not merely an issue of taking up more factory space. A single HBM stack consumes multiple DRAM dies, often 8 or 12 layers, and eventually 16.
Furthermore, because one flawed layer can ruin an entire expensive, meticulously aligned stack, manufacturers have to screen and select known good dies before assembly. The more layers you combine, the more unforgiving that compound yield becomes. You are feeding vastly more raw wafers into the front of the manufacturing process just to get a working HBM unit out the back.
The industry projections illustrate this wafer crowd out clearly. By the end of 2026, HBM is expected to consume roughly 22% of total DRAM wafer input globally, while delivering only about 9% of the actual delivered memory bits. And that divergence is accelerating as the stacks get taller and more complex, because the yield challenges compound with every additional layer you add.
By the end of 2027, forecasts suggest HBM could consume up to 30% of the total wafer input to produce just 13% of the global bit volume. When fabs dedicate nearly a third of their capacity to producing HBM for AI accelerators, it fundamentally reduces the factory capacity available for standard DDR and LPDDR. This massive allocation of raw wafers to HBM creates a structural scarcity of standard memory, which is exactly why AI memory demand can raise the prices of memory in everyday personal computers and mobile phones. We need to look at how compute, the interconnect linking the chips, and HBM operate as essential complements. During the pre-training phase of a massive model, the process is primarily constrained by raw compute and interconnect speed.
However, HBM capacity plays an absolutely critical role during training. The high bandwidth memory has to hold the model weights, the constantly updating gradients, the optimizer states, and the activations. If you lack enough HBM capacity, training a frontier-scale model becomes far less efficient and much harder to parallelize.
When we shift to inference, the usage of the model, the bottlenecks change. The first stage of inference is the prefill, where the system reads and processes the user's prompt. This stage is usually compute-bound.
The second stage is the autoregressive decode, where the model generates its response one token at a time. This generation phase is commonly bound by HBM bandwidth. Whenever a model is processing a very long context window or handling high user concurrency, it absolutely requires substantial HBM capacity to maintain performance without crashing. Let us look at the regulatory text. The United States implemented targeted restrictions in December 2024 through ECCN 3A090. C. This rule restricts the export of high-bandwidth memory that exceeds a memory bandwidth density of 2 gigabytes per second per square millimeter.
It is a precise, technical threshold designed to capture the most advanced memory stacks. There is a narrow exception allowing densities below 3.3, but it requires highly strict conditions, including closely monitored and controlled packaging flows.
This means the most advanced iterations of HBM fall under the restriction. Additionally, the foreign direct product rule extends this reach to Korean-made HBM produced by SK hynix and Samsung. Because their fabrication facilities rely on U.S. technology, equipment, and software, the restrictions apply globally.
It is important to clarify that this rule does not create an absolute technical ceiling. Instead, it radically raises the legal access barrier to leading HBM. It complements the advanced GPU controls, making the required hardware far more expensive and logistically difficult to obtain at the massive scale necessary for frontier training. We have to acknowledge what these constraints do in practice. They significantly raise the financial cost of development, reduce the experiment speed for researchers, and sharply limit the performance headroom of the hardware.
Building frontier models under these restrictions forces labs to operate massive, complicated, heterogeneous clusters. They have to rely on extensive networking and software workarounds to compensate for the hardware they cannot access. These constraints absolutely matter.
We can see this in the performance data. When we examine Kimi K3's own launch documentation, the model is highly impressive, but it still trails Claude Fable 5 and GPT 5.6 Sol across the overall metrics.
Reaching near parity on selected reasoning or coding tasks is a remarkable engineering achievement, but it is not the same as uniform leadership. The hardware restrictions have kept Chinese labs generally behind the strongest U.S. proprietary frontier overall, so these capability leaps are evidence of adaptation under constraint, not unconstrained dominance. Moonshot recently published some detailed architectural insights about Kimi K3, giving us a window into their approach. It is a massive model with 2.8 trillion total parameters, but it operates highly efficiently by activating only 16 of its 896 experts during any given token generation.
It also features a 1 million token context window and native vision capabilities. Under the hood, Moonshot utilizes KDA, attention residuals, and stable latent MoE, which they claim delivers a 2.5 times improvement in scaling efficiency compared to their previous K2 model.
This sparse architecture is one major way they manage massive parameter counts without activating the entire model for every token.
It is vital to note, however, that Moonshot promised the full weights and the complete technical report would be released on July 27th. Therefore, as of our recording today, the complete training recipe, the exact cluster configuration, and the precise data mixtures are not fully known. We are analyzing the published evidence available right now. We can look at published evidence across the industry to understand the broader efficiency toolkit these labs are using. Take DeepSeek V3 as a prime example. It has 671 billion total parameters, but only 37 billion are active during inference. They achieve this through sparse activation, essentially dividing the model into many specialized sectors and only waking the experts selected for a particular token, saving immense amounts of compute and memory bandwidth.
They also utilize FP8 low-precision training. By reducing the mathematical precision of the numbers from 16 bits down to 8 bits, they drastically reduce the memory footprint and the data traffic moving across the chips. Additionally, they employ multi-head latent attention, which is a structural mechanism that dramatically shrinks the size of the KV cache, the working memory a model uses to remember the context it just read.
We also see hardware-aware innovations like dual pipe, which overlaps communication between chips with computation on the chips, reducing the time processors sit idle waiting for data. Beyond that, better optimizer stability lowers the risk of loss spikes and expensive rollbacks during long training runs.
And we see similar efficiency leaps across the ecosystem. GPU's GLM 5.2 utilizes a technique called index share, which essentially reuses indexing calculations for long context tasks, cutting sparse attention indexing flops by 2.9 times at a 1 million context length. Moonshot's Kimi K3 muon clip was trained on 15.5 trillion tokens with zero loss spikes. Furthermore, Moonlight research found that its custom muon optimizer reached parity with Atom W using roughly 52% of the compute in that scaling study. These are ways to turn the available hardware into more learning, not substitutes for hardware itself. When you step back and look at that toolkit, you realize these innovations do not exist in isolation. They form a compounding loop of efficiency. A new architecture combined with extreme optimizer stability allows researchers to push the models harder and longer without crashing. Stable training means longer runs actually finish successfully, producing a usable artifact.
And because those long runs finish without catastrophic failure, researchers can iterate on better data curation and verifiable rewards, which can increase how much a subsequent run learns per flop. Then, they feed those improvements into rigorous testing harnesses, targeting real-world tasks to see exactly where the model succeeds or fails.
That harness feedback immediately informs the next architectural tweak. And when they release these models into the open ecosystem, global developers build better serving frameworks and integration tools, which further lowers the cost of deployment. Dense, rapid iteration cycles allow engineering teams to extract the absolute maximum value from their constrained systems.
But we must explicitly state the hardware gap here. These software and architectural techniques do not magically erase the physical constraints. A lab with an unconstrained cluster can adopt these exact same software efficiencies and push the frontier even further. These techniques mitigate the friction, optimize the available resources, and allow for stunning progress. But the physical constraints of memory bandwidth and compute speed still impose strict boundaries on what can be achieved per cluster. This naturally leads to the question of why Chinese labs seem so unusually prolific right now in publishing these advanced models. We want to answer this directly, avoiding sweeping cultural assumptions. It is driven by a unique combination of structural forces. First, there are multiple, highly capable labs competing fiercely against one another in a very dense ecosystem. You have Moonshot, DeepSeek, Zupu, Alibaba, and others constantly trying to outship each other.
They are operating within a massive domestic market, supported by a deep engineering and manufacturing talent base. There is patient-state capital and aggressive private investment funding these ambitious training runs, providing a long runway for experimentation. The cadence is what stands out. The speed at which they iterate and publish is a direct product of this intense local rivalry.
It is also worth noting that their strategy of open releases creates a continuous loop of global feedback. When they publish open weights, the global open source community immediately tests, integrates, and validates the model, providing free distribution and rigorous debugging.
We want to clearly acknowledge that China is not literally alone in doing this. Labs in Europe, the United States, and elsewhere absolutely build strong, innovative open models as well. But the rapid, relentless cadence we are observing from Chinese labs right now is the result of this very specific domestic competition, meeting the harsh necessity of hardware optimization. Let us explore what happens when these models run on different infrastructure. Identical weights running at matched settings are not retrained or magically smarter simply because they are hosted on a superior server. A fixed digital artifact produces the same fundamental knowledge regardless of the silicon underneath it.
However, better clusters absolutely change the operational reality. Superior hardware significantly improves the speed of inference. It allows the system to handle much higher user concurrency and fully utilize a massive context window without memory failures.
Better clusters also allow operators to use higher precision formats when a higher precision checkpoint exists, and they enable extensive test time compute, where the model can explore multiple reasoning paths.
Direct explanation is key here. If a lab releases only a highly quantized, low-precision checkpoint, placing it on a massive HBM cluster and dequantizing it does not restore the information that was discarded. Superior hardware maximizes the potential of the weights, but it cannot invent data that is no longer there. So what do open weights actually change? They serve as a powerful distribution and business model force after the training is complete. They do not explain how the models were trained in the first place.
When a lab publishes open weights, they enable independent developers and enterprises globally to host the models on their own servers. This unlocks specialized fine-tuning, the creation of custom software kernels, and the integration of diverse ecosystem tools.
It fundamentally shifts the deployment landscape. The intense, constrained innovation occurs during the training phase within the lab. Once the weights are open, that intelligence can be deployed, scaled, and modified by anyone, accelerating global adoption and reshaping the competitive dynamics of the entire industry.
A critical question is whether these open models are actually expanding the total market or just substituting existing usage. We have to add the caveat that we cannot causally label every single new token as purely incremental. Some developers are certainly swapping out expensive API calls for cheaper open models to save money. However, the rapidly rising volume across venues suggests the evidence leans heavily toward these models being additive.
The numbers reflect massive expansion. A report from a 16Z and OpenRouter noted that the platform grew from roughly 10 trillion tokens a year to over 100 trillion, recently crossing 1 trillion tokens per day, with open models sometimes exceeding 30% of all usage. In May 2026, CNBC reported that Chinese models briefly exceeded 60% of OpenRouter token volume. We must state clearly that this reflects a specific developer marketplace token volume, not overall enterprise company adoption.
Yet, when we look at corporate spend, Ramp data showed that model-serving platform use reached 5.8% of AI spending firms, up from 4.5%. Users spent a median of $248 per employee, which is 23 times the median firm, and up 21% month over month.
Crucially, 96.4% of those same firms also paid OpenAI or Anthropic. When you see high co-usage alongside higher overall spend, the reasonable read is that cheaper, varied models are enabling more pervasive AI use, not simply replacing closed APIs one for one. If these models cost millions of dollars and immense effort to train, why release the weights publicly? The strategy focuses on driving widespread adoption and establishing the model as an ecosystem standard.
By releasing the weights, a lab encourages deep community integrations, attracts researchers and developers, and embeds its architecture into countless downstream applications. It effectively lowers vendor lock-in, making enterprise customers far more comfortable adopting the platform.
It is a carefully balanced equation. Openness builds tremendous global influence and software gravity, but it also transfers significant financial value to foreign hosting providers and potential competitors who can run or modify the weights independently.
This brings us directly to monetization. How does an open weight lab generate revenue? The primary engine is their official hosted API. Kimi K3's official hosted API charges 30 cents per million cache hit input tokens, $3 for cache miss input, and $15 for output.
Kimi has highlighted that their Mooncake disaggregated inference system achieves over a 90% cache hit rate in coding workloads, making that lower input price highly relevant for frequent developers.
Beyond the API, labs monetize through specific commercial products. They offer Kimi Work and Kimi Code as paid products tailored for power users and developers. Separately, they provide Kimi Enterprise, which specifically delivers organizational management, data privacy guarantees, and custom deployment support. The open weights act as a global distribution funnel, drawing users toward the API and these secure, paid commercial solutions.
This raises a fascinating operational question. Can China-hosted API providers actually compete for global hosting revenue when foreign clouds possess superior, unconstrained accelerators? The answer is yes, they have distinct advantages. First, they leverage deep first-party optimization. The lab that trained the model can write architecture-aware kernels and optimize their cache economics early and deeply because they intimately understand the system.
They also benefit from relatively cheap domestic electricity, local data residency options, seamless Chinese language integration, and extensive domestic distribution networks. Plus, they offer enterprise deployment support and the earliest access to new official model versions.
But we have to look at the bear case for their hosting margins. Foreign cloud platforms can take those exact same open weights and host them on significantly stronger unconstrained accelerators. This gives foreign hosts the ability to serve global customers with immense speed, vast scale, and broad distribution networks that are already deeply embedded in enterprise IT departments.
Exactly. The foreign hosts might not have the absolute first-party insight on day one, but they have brilliant engineers who can also optimize kernels over time to squeeze out efficiency. This dynamic continually pressures the margins of the original creators and represents the true, ongoing hosting competition playing out across the industry globally. We also have to evaluate the underlying power economics. China's electrical capacity is vast. The country generates more than twice the electricity of the United States. Bloomberg Neff estimates they will add over 6 times as much generation capacity over the next 5 years, a staggering physical deployment of infrastructure.
In 2025 alone, China added more than 430 gigawatts of wind and solar capacity. Initiatives like East Data, West Computing are physically routing this energy to where it is needed, exemplified by a 500-megawatt renewable project directly linked to a Ningxia data center. This massive build-out suggests their relative power advantage. Access to cheap, abundant electricity for data centers looks highly durable for years to come.
Durable does not mean frictionless. Power demand remains heavily concentrated on the East Coast, while much of the new renewable generation is located in the West. Provincial grids can be highly fragmented, making long-distance transmission difficult.
Furthermore, physically siting these massive data centers, integrating heterogeneous chips into unified clusters, and connecting them to the grid is complex everywhere, regardless of national borders. There is also notably low utilization in some newly built data center capacity as infrastructure runs ahead of immediate demand. The power advantage is real and durable, but extracting it efficiently requires overcoming significant physical infrastructure hurdles. It is vital to recognize that no single country needs to win every single layer of the AI stack to succeed economically. We look at this through a 5-layer framework: base models, advanced silicon, energy and hosting infrastructure, domain-specific adaptation, and the application workflow layer. A country can capture immense value without ever training a 3 trillion parameter base model from scratch.
Absolutely. The United States currently leads in the massive closed frontier models and advanced chip design, the top 2 layers. The Gulf can compete in the infrastructure layer through sovereign capital plus abundant solar and gas. The Nordics and Canada offer a different package: hydro or wind resources, cooler climates, and locations suited to efficient hosting.
Moving down to the adaptation layer, Europe, Japan, and Korea are deeply positioned to lead in industrial AI, robotics, domain-specific manufacturing models, and producing the advanced semiconductor manufacturing equipment the rest of the world relies on to build chips.
Meanwhile, in the application layer, India and Southeast Asia have enormous opportunities. They are actively developing rich local language models, executing sovereign deployment strategies, and building vast workflow integrations for global IT services. The pie is deeply segmented, and value accrues very differently in each specific region. The price competition at the frontier is already intense, though we should be very careful interpreting official list prices. They are not directly comparable outcome costs because models differ in token use, retries, latency, and task success. For OpenAI's GPT 5.6 Sol standard, it sits at $5 for input, 50 cents for cached input, and $30 for output per million tokens, with batch processing roughly half that.
Anthropic's Sonnet 5 has introductory pricing through August 31st at $2 for input and $10 for output, while Opus 4.8 is $5 and $25. XI's Grok 4.3 below a 200K prompt is priced at $1.25 input and $2.50 output, with Grok 4.5 at $2 and $6. The closed frontier models are actively undercutting one another, not just reacting to open weights.
And Kimi K3 comes in at $3 and $15, with cached input at 30 cents. What we are seeing is that frontier labs are competing intensely by segmenting the workloads. They offer caching structures for repetitive tasks, batch flexibility for offline data processing, enterprise bundles, and highly efficient mini-tiers for fast, simple routing. The list price is only the starting point for calculating the real workload cost.
As the access price for base models compresses, the enduring moat shifts heavily toward reliable task completion and intelligent routing. Developers are increasingly calculating the outcome-adjusted cost rather than the raw per-token cost. You might route a query to a cheap, fast model first. If it fails or the confidence is low, you automatically escalate to a heavier frontier model.
And if that frontier model fails, the system routes it to human review. Achieving fewer retries and delivering highly consistent, accurate outputs on the first attempt is what makes a model truly valuable in a production environment. Integration and broad, seamless distribution become a massive defensive moat against commoditization.
Organizations are ultimately paying for integrated tools, reliable testing harnesses, seamless data integration, low latency, and guaranteed uptime. They want enterprise trust, liability indemnification, and strict compliance standards applied to their proprietary data.
This creates a fascinating financial dynamic. Unit price pressure can continue even while overall usage expands rapidly, so total industry revenue can rise at the same time. The harder question is whether margins and the massive contracted capital expenditure required to train and operate these models can adjust just as quickly. Let us tie this back to the broader memory market and CXMT. Currently, CXMT holds roughly 7.7% of global DRAM revenue share and recently executed an $8.55 billion IPO.
They are manufacturing credible DDR5 and LPDDR5X memory, though they are not producing frontier HBM at volume. Their focus is firmly on the conventional memory tiers.
If conventional DRAM expansion from CXMT and others continues, it has the potential to relieve memory prices for everyday devices and servers. The added supply could compress conventional DRAM pricing and margins across Micron, Samsung, and SK Hynix in 2027 and 2028. That pressure could materialize in the conventional market even while frontier HBM qualification remains a distinctly separate and difficult hurdle.
We always aim to steelman both sides of the argument before we conclude. The case supporting hardware constraints is that they preserve a costly hardware lead, making the absolute highest capability ceiling harder and more expensive for competitors to reach while consuming time on workarounds.
The counter case is that extreme architectural efficiency narrows selected capability gaps remarkably well, while open models broaden overall global usage, attract developers, and pressure pricing power across the ecosystem.
Moving forward, the observable questions we are tracking are very specific. First, does an independent, measurable capability gap persist across the hardest general reasoning benchmarks? Second, how does the true outcome-adjusted cost per successful task evolve between closed and open systems as routing gets smarter?
Other observable measures are the ratio of open to closed co-usage within actual enterprise deployments, the physical utilization rates of China's newly constructed data centers, and the capacity and pricing movements in the conventional DRAM market. Together, those measures can help distinguish durable structural change from a temporary burst of releases or pricing. Pulling all of these threads together, the core reality is that hardware restrictions are very real and actively binding. They reshape the physical supply chain and force profound engineering adaptations. However, advanced capability is not merely the product of unconstrained hardware. It is produced by a complete system encompassing compute, memory bandwidth, sparse architecture, training stability, and intense domestic competition.
Open weights then serve to widen the distribution of that capability, pulling developers into the ecosystem and intensifying the business model competition worldwide. Physical inputs absolutely still matter. They set the ultimate boundaries of speed and scale, but the intelligence value chain is fracturing into distinct, specialized layers that reward different approaches.
No single country or laboratory is required to capture every part of that stack to remain highly relevant and capture economic value. The efficiency advances developed under constraint can continue to pressure frontier margins, even as the raw capability ceiling keeps moving higher.
It is a remarkably complex, rapidly evolving map, and one we will continue to carefully measure against the physical realities of the silicon. We appreciate you exploring the mechanics of compute, memory, and model economics with us today.
That's a wrap. If this was useful, follow or subscribe for the next one, and tell us where we're wrong. Thanks for listening.